questions about is the CC, really content, for example. So I asked Joe, who was a postdoc here, and just recently, like a month ago, I kind of started at Brookhaven to give an overview of data modern cosmology. So, thanks for doing this.
Yeah, it's really nice to be here, talk to a bunch of people I don't normally talk to, so yeah, this hopefully will be interesting for both you and me. I'm a staff scientist at Brookhaven National Lab, but I'm still located in the Bay Area for the next year, so you can come and find me at LBNL if you want to come ask me questions or shoot me emails at this address. And so I'm going to be telling you about inferring fundamental physics from large-scale structure, in particular in light of the DESI 2024 results. So just a quick disclaimer before I jump into the talk. This is an overview of topics in cosmology that I find particularly interesting and robust. That means it's a subset of all of the things that are interesting and robust in cosmology, particularly biased towards large-scale structure and the cosmic microwave background, which are the things that I think about most. And it's going to be organized by kind of recent and upcoming DESI results, but I'll make a few brief excursions. So here's an outline of the talk. I'll start with some preliminaries of the standard model of cosmology. I think maybe that's a bit pedagogical for this audience, but just to set the stage and some tensions, and then I'll tell you a little bit about the dark energy spectroscopic instrument, or DESI, how it works and how we make measurements very briefly, and then I'll jump into some of the results. So released results are the baryonic acoustic oscillation measurements that we put out in the spring. So these are kind of an exquisite probe of the metric and expanding history of the universe. And then, so that'll be kind of the bulk of the talk, and then I'll break down the rest of the talk into two different pieces, talking about probes of the growth of large-scale structure, and then also kind of early universe physics at the very, very end if I have time. Okay, so let's jump in. This is kind of an obligatory slide for any cosmology talk. The standard model of cosmology, the story that we tell goes a little something like this. We have quantum fluctuations that are produced in the very early universe that we think are made macroscopic during this process of accelerated expansion that we call inflation. Those macroscopic fluctuations are then imprinted on the cosmic microwave backgrounds. This is the photons that we observe that are coming from the surface of blast scattering when electrons and protons first combine into neutral hydrogen. And these fluctuations, we think, then grow into all the structure that we observe in our galaxy surveys and observations of the universe today. And we think that that growth of structure from those early fluctuations into those galaxies and stars and so forth is driven largely by the presence of dark matter. So this is this thing that we have very little idea what it is, but we know it doesn't interact strongly with anything other than basically through gravity. And then at the very late times, we have another period of accelerated expansion that we kind of know exists through a variety of means at this point. And we don't have a fundamental physical explanation for this, but we posit that it is driven by another component of the energy density of the universe that we call dark energy. We think that is a cosmological constant, but as we'll see later in this talk, there's maybe some interesting hints that it might not be from recent results. So how did we come about this picture? So I'll give you a brief aside about how we do inference in cosmology and large-scale structure in general. So we think that because all of the structure of the universe is sourced by this stochastic quantum process in the very early universe, the predictions that we make have to be statistical in nature. So we don't make predictions for like the position of the positions and velocities of galaxies. We have to make predictions for summary statistics. And so what does that look like in practice? Well, in general, it usually involves making a map. So I'm showing one such map here on the left-hand side of this slide. So this is a map of dark matter from a simulation, where I'll show a few maps like this. It's not showing up super well on this projector, but the angular direction here is just angle on the sky, and then the radial direction is direction along the line of sight. And so we take these maps, we Fourier transform them, and then measure endpoint statistics from them. So one's the 2-point function or the power spectrum is shown here on the right, so then the y-axis is just this power spectrum, so it's the ensemble average of this overdensity field Fourier transform, and the x-axis is the modulus of the wave vector. So this is just inverse distance. So I'll be showing things that look like this a lot, and so yes, this is the matter power spectrum, and we'll be taking power spectra of galaxies a lot in this talk. And so most of the progress that we've made in large-scale structure comes from making these measurements and then building models for them given given a cosmological assumptions about the cosmological model, and comparing those models and those measurements. We've been doing that for quite some time, and I think this slide kind of nicely summarizes from a kind of bird's eye view where we are in cosmology today. So the right-hand plot is showing measurements of this linear matter-power spectrum from a variety of different experiments. So the blue, orange, and green points here are measurements coming from the Planck cosmic microwave background satellite, and the rest of the points on this figure are coming from low redshift galaxy surveys. So you can see there's a large dynamic range on these measurements, and the black line that is shown here is the best fit lambda full dark matter model to these to the cosmic microwave background measurements only. And the thing that I want you to observe is that although this line is only fit to the CMB data, it actually very well describes the low redshift galaxy survey data.
Do you get anything more by adding mass?
Yeah, we do. So the act gives us, the temperature measurements are not really competitive. In polarization are not super competitive with Planck, but the lensing measurements are what we get from ACT, and those are really, really interesting. And I'll talk very briefly about them later. So this is a 2018 figure, so that's kind of, ACT, I think the big lensing results came out last year, basically. And they're still coming, yeah. And so DESI is actually doing a lot of cross correlations with ACT and things like that, which I'll touch on at the end. So yeah, this model gives us a very precise measurement of the energy densities in the universe. So we think there's about 27% dark matter, 5% normal matter, and about 70% dark energy. But this leaves a bit out. In particular, I think some of the most interesting aspects in cosmology right now are these tensions that are popping up between the measurements from the CMB and lower redshift measurements. So the most well-known of these tensions is the so-called Hubble tension, which is a discrepancy between the measurement of the local expansion rate of the Hubble constant made by using so-called direct measurements of the Hubble constant coming from the distance ladder. So this is like looking at things like parallaxes and then Cepheids and then type 1a supernovae. I'm not going to talk about this methodology really at all today, but when you put all those measurements together, you get a measurement of this local expansion rate of the universe that is significantly higher than what is preferred by measurements from the CMB that then use the lambda CDM model to extrapolate the expansion rate from the expansion rate at the surface of last scattering to redshift 0. So that's what this gray contour here is. And so you can see there's a 4 or 5 sigma discrepancy between this gray contour and this distance ladder measurement. And the thing I'll talk a lot about today is how the DESI, in particular spectroscopic surveys, can weigh in on this through a method called measuring baryonic acoustic oscillations. And I'll give you a lot of detail about what that means in a bit. And the other tension that is starting to become more interesting is the tension between, again, the local measurements of the matter-power spectrum, the amplitude of the matter-power spectrum. This is a parameter that's called sigma 8. It's just the normalization of the matter-power spectrum at 8 megaparsecs, basically. So measurements of that using galaxy surveys at low redshift, and again, predictions for that redshift 0 amplitude that we can make by making cosmic microwave background measurements and extrapolating them to low redshift using that CDM. I'm not going to make any value judgments about whether these tensions are real or not right now, but I will say that this is the kind of thing that gets cosmologists excited, because this is the exact sort of thing that you would expect to see if there's some incomplete piece of this lambda CDM model, which we kind of know there has to be, given that there's these two big phenomenological pieces that we don't understand the fundamental physics of. And so the hope is that we can kind of precisely measure these tensions, and as data gets better and better, the systematic and statistical errors will go away, and what we'll be left with is hopefully fundamental physics-driven tensions that we can then use to learn about the properties of dark matter, dark energy, neutrinos, inflation, so on and so forth.
What's the voting axis in this local?
So that's the local, these direct measurements of the Hubble constant using Cepheid stars and type 1a. This one.
Direction.
Oh,
the
the
y-axis.
Oh, this is the sound horizon, which I'll explain in quite a bit of detail later. And so the reason it's on this plot is because the baryonic acoustic oscillations measure the degenerate combination of this and the Hubble constant, and then that can be used to weigh in on this section. Right. So what does DESI add? So DESI can actually weigh in on both of these tensions. And so on the Hubble tension side, these baryonic acoustic oscillation measurements provide a very precise extra data point in this picture that I was just showing you. These BAO measurements also provide a great deal of other information that I'll talk about in detail. And we can also measure the growth of cosmic structure over time, so the evolution of the matter power spectrum or the matter field in general over time, using DESI and combinations of DESI with other things like actolins. And so I'll talk about both of these today, again, mostly highlighting the baryonic acoustic oscillation results, but also telling you a little bit about some early DESI results from this growth of structure side, and then what to look forward to in the next month or so. So yeah, jumping into some of the details now. DESI is a fiber-fed multi-object spectrograph. It has robotic positioners that place fiber optic cables on the positions of galaxies in the sky, and then the light from those galaxies is fed down those fiber optic cables to spectrographs that disperse the light. So there are 5,000 of these fibers and robots on the focal plane. It has an 8 square degree field of view, which is quite large compared to any other spectroscopic survey to date. And it has 10 3-channel spectrographs, and it's in the process of observing 35 million galaxies over 14,000 square degrees, which is about a third of the total area on the sky in 5 years. So the 5-year survey will be done in about a year and a half. So how does this work in a nutshell? So really high level overview of how this works. The first thing that we need is our images of the sky. These are taken with other telescopes, and they tell us where we can actually look to find galaxies that we can measure distances to. And then we have to pick out the galaxies that we actually think we can measure precise distances to. So the circles that are being drawn around these little smudges on these images, the smudges are galaxies, are the galaxies that DESI has selected to then go and measure precise 3-dimensional positions of. And then we point DESI in the sky and align the fibers. We use these robots to position the fibers on the galaxies. The light from the galaxy goes down the fiber into the spectrograph, which disperses the light as a function of wavelength and allows us to measure emission and absorption features in the galaxy light. So these are galaxy spectra. And if we can identify the emission or absorption feature, in particular what atomic transition is causing that as emission or absorption, then we know the rest frame wavelength of that emission or absorption. We can measure the observed wavelength of that emission or absorption feature, and the difference between those two divided by the rest frame wavelength tells us the redshift of the galaxy, which then tells us how much the universe has expanded since the light from that galaxy was emitted.
What determines which galaxies you pick?
So we have a good, basically we're looking for things that have very prominent very prominent emission and absorption features, like the ones that you see here. So this is a quasar, which is supermassive black hole spewing out a bunch of stuff, and it has a very strong Lyman alpha line, this one here. And so we can easily identify what that line is, and then we can use it to measure these redshifts. And so we're looking for galaxies that we think we can unambiguously identify some emission or absorption feature.
Other finding some sort of standard candle.
I wouldn't call it a standard candle, but actually DESI was designed to find oxygen to the oxygen 2 emission line, which is just the transition between and so that's a doublet. There's a rotational transition. And so the resolution of DESI is actually determined so that we can identify that doublet and unambiguously identify that emission line and then use it to measure redshifts.
Is that because you can measure especially precisely the redshift for that?
Well, it's because you can, if basically, if all you see is that doublet and nothing else, and basically the rest of the spectrum is noise, then you know it is this O2 emission line because of because it's this doublet that basically can be unambiguously identified as such.
I guess I'm trying to understand what makes that doublet so special compared to, I mean, you were pointing at
So it's just that it's a very strong feature in star-forming galaxies because star formation ionizes oxygen and causes this emission feature to be particularly strong. So it's just kind of an empirical fact that this is a very strong emission line in a very large number of galaxies.
and the fact, I would have naively thought maybe oxygen is not, I mean, hydrogen is much more abundant, so
Yeah.
it would be easier to see.
So hydrogen is certainly, I mean, so these quasars, this Lyman alpha line is hydrogen, and so we're using that as well. There's a couple of different types of features that we use. So it's not just these other two things. It's some hydrogen emission line. It's So there's a whole. I'm actually not people can talk to you for days about this sort of thing. I'm more like a theorist / data analysis. There's go talk to David Schleichel if you want to learn about this for an indefinite period of time. But yeah.
Is there a selection effect associated with this?
They're not these particular features, but there are worries in future surveys that there are some selection effects. So like follow-ups to DESI are going to be targeting very faint galaxies that are actually looking at this Lyman alpha, the different type of Lyman alpha emission line, where there are radiative transfer effects that can depend on the density of gas along the line of sight that then causes bad things to happen. So that's a worry going forward. The selection effect that we actually do have to worry about more is, if you have a really dense clump of galaxies that you've targeted to actually get these get redshifts of, you can only get if there's 100 in one of these little circles, then we can only get one redshift at a time, and so we're missing 99 galaxies, and so you're actually this is something that is dependent on the density of galaxies, and so that is something we have to worry about. It's called fiber collisions, or so yes. So other important systematic effects, kind of on a more theoretical side. So we're making 3D maps of galaxies. And these 3D maps of galaxies, we're going to try to use to measure these periodic acoustic oscillations. But the thing that we can make really precise predictions for with basically zero free parameters other than our cosmological parameters is the density of matter and matter power spectra. But galaxies are not faithful tracers of the matter distribution. They're what we call biased tracers of the matter distribution, and that's because they form in the most overdense regions in the universe. And so this imparts an effect that we call galaxy bias, which just means that if you measure the power spectrum of galaxies, which is this orange line here, and compare it to the power spectrum of dark matter, you get a very large difference between these two. That is just kind of an astrophysical effect that we have to marginalize over. We don't have a fundamental description for how this works. So that's the price we pay for dealing with galaxies. And there's another very important effect that happens in these spectroscopic galaxy surveys that's called redshift space distortions. So this is an effect that is imparted by the fact that when we measure a galaxy redshift, we're not only sensitive to the expansion of the universe since that light was emitted, we're also sensitive to what we call the peculiar velocity of the galaxy, which is just the velocity of that galaxy with respect to the bulk expansion of the universe. So that imparts another additional red or blue shift to the galaxy redshift that we measure, that then serves to kind of smear out structure along the line of sight in overdense regions, where there are large thermal velocities of galaxies kind of orbiting in clusters. So this breaks the isotropy of the maps that we make, as you can see maybe in this figure here on the projector. So if we measure the power spectrum of galaxies along the line of sight versus the plane of the sky, we get two different things. So the plane of the sky gives us just positions of galaxies, so we're just measuring the density of galaxies, whereas along the line of sight we're measuring some combination of densities and velocities. So this is both a nuisance and is actually going to help us later on in a way that I'll describe. Okay, so that was how DESI works in a nutshell. Now we jump into some of the results. So first I'll talk about baryon acoustic oscillations, and this is largely going to be following the paper that we put out in the spring of this past year. So why do we care about baryon acoustic oscillations? Well, first a bit of background about our metrics. So, we think we live in a homogeneous and isotropic universe, at least on the very largest scales. So Friedman-Lemaitre Walker-Robinson metric describes this universe, and then we treat large-scale structure as perturbations of this metric, so these size and pies here, we have observations which basically tell us that the universe is flat to a very, very good approximation. And so that means that in order to determine the metric as a function of time, we just need to measure this A, which is the scale factor of the universe, so how much the universe is expanding over time. And so by measuring this A, we can really constrain a lot of interesting physics that I'll talk about in just a second. And the best way of measuring the scale factor is by measuring distances as a function of redshift. So redshift is just 1 over A minus 1. And the best measurements that we have of distances come from so-called geometric probes. So this works as follows. If you think you know the size of some object in the universe, in this case it's going to be baryon acoustic oscillations, then you can use it as a standard ruler. So you know the physical extent of this object. You measure its angular extent on the sky, and those two things then give you the distance to that object. So if you then know the redshift of that object, that gives you, the expansion history of the universe as a function of redshift.
We should know the size of an object.
Yes. Actually, that's exactly what this next slide is. So this is why BAO are so powerful. It's because we can basically predict the size of this feature through very, very simple physics. So what happens is, in the very early universe, perturbations enter the horizon. And so there's a perturbation that is, basically just dark matter, gas, photons, neutrinos. It enters all at once. So in the very, very early universe, the temperature is high enough so that the photons and gas are very tightly coupled in a plasma. And so what that does is it causes a pressure wave to expand outwards. And that pressure wave continues to propagate out in spatial extent until the time at which electrons and protons can combine into neutral hydrogen. And then the photons just free stream out from these potential wells. But what's left is this characteristic feature in the gas that is the extent to which the pressure wave could propagate outwards in between the time it entered the horizon and this time of recombination. So it looks a little bit like this. So you have a perturbation, delta function at radius 0. The gas is blue, the photons are in red, and what you see is that, let me run this back, is that at early times they're propagating out together, but then at recombination the photons just free stream out, and the gas is left here with this characteristic peak. And then as time evolves forward, gravity causes this perturbation to grow on small scales, but this imprint of this pressure wave is still left on these very large scales. And so using very basic plasma physics and just the expansion and our understanding of how the universe expands over time, we can determine the scale of this feature. So basically it just depends on this integral here, which is the distance that sound wave can travel between redshift infinity and the redshift that the photons and baryons decouple. This is the so-called drag redshift. And so it's just this interval of the sound speed over the Hubble, over the expansion rate of the universe as a function of redshift. And the sound speed we can determine through very, very basic plasma physics. It just depends on the baryon-photon ratio. And the expansion rate depends on kind of parameters of interest of the cosmological model. So it depends on matter density, the radiation density, curvature, energy density, and the energy density. So by measuring this feature, we can then learn about And so the first place that this feature was measured is in the cosmic microwave background. And so that's what I'm showing here is the angular power spectrum of temperature and isotropies in the cosmic microwave background as measured by Planck. Those are the red points. The blue line here is just a lambda CDM prediction for this spectrum. And so this is a harmonic space spectrum, but if you were to Fourier transform it, you would see it as a single peak, but in harmonic space, but it shows up as multiple peaks. So by measuring this peak, we can determine what RD is, and then learn about all these. We learn about the statistics. So we can do something analogous with galaxies. Like I said before, the gas has this imprint in it, just the same as the photons do, and the gas then collapses and forms galaxies. And so this pressure wave feature is imprinted on the distribution of galaxies as well. And the galaxies come with a nice additional aspect, which is that we can measure their three-dimensional distribution. We can kind of measure this feature as a function of time, but also we can measure, at a given time, we can measure this feature kind of in a three-dimensional spectrum rather than just the angular spectrum I was showing you. So we can kind of measure two different characteristic scales. One is in the plane of the sky, so we can identify this feature as a characteristic separation in angle. And then that angle combined with, measuring that angle basically tells us the ratio of the size of the sound wave to the distance of the co-moving distance of that galaxy's sample. And then along the line of sight, we can measure a characteristic separation in redshift, and that tells us actually something about the expansion rate, h of z. And so we go ahead and measure this periodic acoustic oscillation feature in the correlation function or power spectrum of galaxies at a bunch of different characteristic redshifts, and that's what's being shown here in this figure. So these are actually the correlation functions of galaxies, and you can see this characteristic bump. So this is just the Fourier transform of that power spectrum I was talking about before. And this bump is kind of very easy to identify in these measurements. That's about 150 megaparsecs. And so we can do this as a function of redshift, and by doing so we can constrain this scale factor as a function of redshift, which then gives us information about these energy densities of all these components in the universe. And so another really nice aspect of this is that although I was telling you before about how we have this nasty galaxy bias effect that makes it such that the galaxy distribution doesn't follow the matter distribution, this feature is relatively protected from any sort of kind of non-linearities or galaxy bias in physics. So there's kind of been exhaustive studies of these contributions to the error budget from these measurements from theoretical, so-called theoretical systematics related to these galaxy biasing effects, non-linearities, and they've been shown to be very, very small effects, so at the 0.1 to 0.2% level. And DESI is hoping to eventually constrain this periodic acoustic oscillation feature to about the 0.2% level. So we'll have, at the end of the day, after the 5-year survey, we'll have statistical errors that are basically on par with the systematic errors, which is So these are the actual results. So now I'm going to show you results quoted in two different ways. So one is something called an isotropic size of the BAO. So this is just the measurement that we get when we average over kind of all three dimensions at once instead of splitting things up along the line of sight in the plane of the sky. We quote things in terms of an isotropic size of the BAO and a ratio of the plane of the sky to the line of sight measurement, just because these are kind of less correlated than just looking at the line of sight versus the plane of the sky due to the way that we measure these things. I can go into details if you're more interested. So this left-hand side shows the isotropic size of the baryonic acoustic oscillations, and the right-hand side shows the ratio of the line of sight to the plane of the sky measurements. The dashed lines here are predictions for these quantities as a function of redshift, assuming the best fit lambda CDM model from the Planck experiment, and the solid black line here shows the best fit lambda CDM model of these measurements. Okay. So even without external information about the size of the sound horizon that comes from knowledge of this plasma physics I was talking about in the early universe, we can constrain interesting things using these measurements. And that comes from the fact that these measurements at different redshifts, so coming from different galaxy samples, constrain a degenerate combination of omega matter, so the matter density, and this combination of the sound, the sound scale and the Hubble constant. The degeneracy direction changes as a function of redshift because these have different effective redshifts, so they're basically probing omega matter and H of Z at different redshifts. And so by combining all these things, you can break these degeneracies and get a very tight constraint on the matter density of the universe. That's what's shown here in black, and then over here compared with previous measurements of this from the Sloan Digital Sky Survey, and then also compared with the cosmic microwave background. So you can see the DESI results prefer about a 1.5 sigma difference between omega matter and from what the cosmic microwave background constraints prefer. And so this is completely consistent with statistical fluctuation.
In order to get these constraints on omega n, do you need to assume lambda CDM, lambda CDM?
Yeah, so this does assume lambda CDM here.
Specifically flat lambda CDM.
Yeah. So you still get I think basically what happens if you don't assume lambda CDM is the width of this degenerate of these contours of this direction grows, and so you just get a weaker constraint, but you can still, this degeneracy breaking effect still happens, so you still do get an omega matter constraint if you open up the parameter space to something else, but it does degrade the constraining power a little bit. So then what happens if you add in information about what this sound scale is? So we can do that in a few different ways. So we can use Big Bang nucleosynthesis calculations combined with measurements of the deuterium to hydrogen ratio and the helium to hydrogen ratio. And that tells us basically what the baryon, using that information we can get an external constraint on what the baryon density is in the universe. And we know what the photon density is in the universe by measuring the temperature of the CMB. And so that gives us basically an external prior on what this sound scale is, this drag scale is, and combining that with the VAO then allows us to measure H0 directly. So we can also include the angular size of these features in the CMB, so this theta star parameter, which is thought to be basically kind of the most robust measurement that we can make from these CMB spectra. So if you don't trust other things in the CMB, you should trust this probably, and so we can combine with this. And then if you really do trust kind of all the CMB information, you can combine with the CMB constraint on what RD is. And that gives you the green contour here. And so you can see all these are pretty consistent and give you a value of H0 that is a little bit larger than what's preferred by the CMB alone, but still significantly smaller than what these direct measurements prefer. Although there have been some recent developments in these direct measurements showing that maybe there are some systematic errors, and in particular, a paper that just came out that uses the James Webb Space Telescope to measure these things using 3 different types of calibrations shows kind of 1 to 2 sigma discrepant constraints on this. All these are all different ways of measuring H0, but all direct, so-called direct measurements. And so there's some kind of poorly understood systematics in these measurements still, at least this is my take, that are kind of reason to maybe not believe so much in this tension and to believe the CMB/VAO results on this. Okay, now jumping into dark energy. How am I doing? One of the kind of highlighted results that came out of these DESI papers was constraints on the dark energy equation of state. And so in absence of kind of a good theoretical model for what this equation is, what dark energy is, we have a very phenomenological parameterization of how it evolves over time. So we just say some constant plus some time evolving piece that looks like Z over 1 plus Z. And so we can constrain these parameters using these distance measurements. from the BAO, and the DESI results alone are shown in dashed black here. And so these kind of look worse than they are in terms of preferring maybe non-lambda CDM, non-cosmological constant, which are these crosshairs here. But there's something that's called a projection effect that's shifting these contours kind of away from the maximum likelihood value of the contours. And so if you look at just a delta chi-squared between the best fit lambda CDM model and W naught WA model, you only see a delta chi-squared of about 3 with the designated amount, so that's, you know, not very large. When we combine with the CMB, yep.
I mean, I don't know why this is not said more often, but if you only, we can introduce as many parameters as we want here.
Yeah.
But if you only introduce W naught,
Yeah.
if you only use DESI, even if it's better than I think you can add almost exactly on.
Yeah.
Minus 1 with like 2% error or something.
Yeah.
I mean, it's unbelievably good. Right?
It is really good. So what I'll say about that is, so yeah, I mean, it's a weird coincidence actually that our W CDM constraints do come out with W minus 1, but W naught WA do prefer, you know, this deviation from cosmological constant. And part of that has to do with the fact that, you know, the WCDM model is a little bit restricted in kind of what the growth histories are. And so, you know, there are some fluctuations that you can see in these measurements that basically don't project on a change in a constant W, but do project onto a change into, you know, this time evolving equation of state. And so, yeah, I mean, I'm very hesitant to really say there's anything, you know, incredibly exciting about these this preference for non-cosmological constant dark energy. Partially because the DESI results alone, even in this space, you know, don't really show any evidence, but also because, you know, so you combine with CMB, this delta chi-squared gets closer to 10. It's really only when combined with supernovae that you get these really big deviations. And as you can see, the supernovae themselves, these 3 different supernova analyses kind of prefer somewhat different things, and there are, you know, reasons to believe that the supernova calibrations of some of their systematics are kind of underestimated. There are papers by supernova folks looking into this quite extensively now, so I would definitely caution to take these results, the combinations with supernova data with a grain of salt, at least for now.
I mean, you have to cherry pick a particular catalog to get really to 4 sigma, right?
Yeah, exactly. Yeah, so yeah. But DESI alone combined with CMB at the end of the survey, if there's, you know, the size of the tension that we see, or the size of, you know, this discrepancy between lambda CDM that we see now, we will detect it at, I think, the 3-ish sigma level with DESI and CMB alone without supernovae by the end of the survey. So I would wait for that. I trust the BAO results much more than I trust the supernova results, but I'm not a supernova person. I was actually when I was an undergrad, but yeah, not anymore. Okay, so moving on, another of the kind of results that got a lot of press from this paper was the constraint on neutrino masses. So the way that we get neutrino mass constraints from these measurements is by basically measuring the expansion history. So the neutrinos are relativistic at the surface of last scattering, but in the DESI results, in the redshifts that DESI probes, they're non-relativistic, and so they contribute to the expansion rate as radiation at early times and matter at late times. So this imparts a characteristic signal in this expansion history of the universe that we can then constrain with BAO. So the CMB alone, or the CMB alone constraints on some of the neutrino masses are shown in blue without lensing and orange combining with lensing. And then with the BAO data are shown in green here. And then this is just the degenerate. There's a degeneracy between a neutrino mass and H naught that is largely broken when you combine with BAO. And there's an additional effect that comes from that neutrinos impart that comes from the suppression of the growth structure that I'll talk about in just a second. But the thing that I'll say about this is that these results are a bit Plyer dependent at this point. So the fiducial results just assume that some of the neutrino masses are larger than 0 eV, but imposing, you know, the normal hierarchy gives you a larger upper bound, so it gives you, this about 0.1 eV constraint, and this is also combining with CMB. But either way, we're kind of putting some pressure on the inverted hierarchy. there are a few papers out there that are claiming that we've detected a negative neutrino mass, like this one here, and I would say that this is better phrased as a low redshift preference for a higher omega matter than what is preferred by the CMB, or higher omega matter, or different constraints on Hubble parameter as well. So phrasing this as a negative neutrino mass is kind of a really weird, unphysical way to look at this, I would say. So it's really just driven by the fact that DESI prefers a smaller value of omega matter than the CMB predicts, and that's kind of the opposite of what you would expect given how neutrinos evolve over time, and so that's where this negative neutrino mass comes from.
So are there models of slowing down the
Actually, the other thing is, these combine with CMB lensing constraints, and the CMB lensing, the amplitude of structure measured by CMB lensing is actually larger than what we get from the CMB by a little bit. And so that's the other thing that's driving this negative neutrino mass constraint. So negative neutrino is like you would expect a suppression, but we actually don't observe really any suppression so far. But it's these are all kind of consistent with statistical fluctuations at this point. Okay, so I will just briefly touch on growth probes since I'm running out of time. I'll phrase this in terms of neutrino mass, but measuring the growth rate of structure is a kind of interesting thing to do in general because there are a variety of things that can impact how much structure grows over time, not just neutrinos. But we can basically factorize this matter power spectrum into different pieces. So one, this growth factor D that encodes the post-recombination growth of structure. That's the thing that we're going to be interested in. And then a transfer function that encodes physics between recombination and inflation, and then this inflationary piece. So we can basically, given some recipe for all the things that are in our universe and the expansion rate of the universe, we can solve the Loss-Poisson equation and we can get the growth factor as a function of scale and time. And at linear order, the free streaming of neutrinos imparts a scale dependence to this growth factor that otherwise isn't present. This is the thing that's often thought of as being where we get neutrino mass constraints, but that's actually a kind of false claim. The real dominant effect, and so that's because the free streaming scale of neutrinos is so large that it's not really the scales that we probe in these surveys. The dominant effect is really just a scale-independent suppression of the growth that depends on the mass fraction of neutrinos and the redshift at which they go non-relativistic. And so we can then go ahead and try to measure how much structure grows over time. This is complicated in a large part in these galaxy surveys by this galaxy biasing effect. I won't say really much about, so basically we can perturbatively expand this effect on large scales, basically only allowing for operators that obey the symmetries of our problem. And if you do that, then you can write the galaxy in terms of the matter density with some free coefficients. And we can formulate this as an EFT to remove UV sensitivity. But if we just observe the galaxy density, then you can see from this equation that at linear order, this is perfectly degenerate with this matter density here. This galaxy bias B1 is perfectly degenerate with the matter density. And so by just measuring galaxy densities, we can't get any information about the matter densities. But luckily, as I was saying early in this talk, these spectroscopic surveys also are sensitive to the line of sight velocities of galaxies through these redshift-based distortion effects. And so that means that, and the velocities are guaranteed to be unbiased on large scales with respect to the matter. And so basically we can write down the galaxy density in these redshift distorted coordinates that are denoted by S as the real space galaxy density plus something that depends on the line of sight, angle to the line of sight, times the velocity divergence, which just depends on the growth rate of structure. So I have this growth factor, the derivative of the growth factor so we can get a handle on the growth rate by measuring these redshift space distortion effects. I won't tell you much about how that works, But I will tell you that we have DESI results coming about this soon. There are results about this, I know from previous surveys, in particular this Baryonic acoustic oscillation survey, BOSS, that use this technique to constrain the amplitude of the matter power spectrum to be about 2 sigma low compared to the predictions from Planck, so shown in black here compared to the blue and red contours here. So these results have to be taken with a bit of care because these bias expansions are very degenerate. This biasing effect is very degenerate with cosmology in a way that causes one-ish sigma shifts when we look at just these posteriors marginalized over all of our nuisance parameters. So these posteriors are shifted by about 1 sigma by this effect. So there's really kind of not significant evidence for attention here, and DESI will weigh in on this very soon. Actually, in this month, I think we're hoping to release these papers. And then I'll say that the premier results on the growth of structure from DESI will come from combining complete lensing, so both from measuring the distortions of galaxy shapes to measure the matter distribution, as well as measuring the distortions of temperature and anisotropies in the cosmic microwave backgrounds. These are 2 ways that we can measure weak lensing. That tells us about tells us about the matter distribution more directly, although not fully directly. And so there's some early results out. This is actually where I spend a lot of my time. So this is a galaxy lensing combined with DESI result showing consistent sigma 8 with Planck, and then this is a CMB lensing version. Similar analysis using CMB lensing combined with DESI, not including redshift space distortions yet. That shows a slight preference for lower sigma 8, so that's this purple line compared to this black line, which is Planck. Okay, and I think I'm out of time, but I'll spend 1 minute talking about pros of inflation. So this is something that people are getting really excited about. It's something I don't work on really at all. But given the audience, I figured maybe it's useful to spend 1 slide on it. So we can probe primordial non-Gaussianities primordial non-Gaussianities that look, we can probe primordial Gaussianities through something called scale-dependent galaxy bias. So if there's some nonlinear contribution to the primordial potential that looks like this, multiplied by some free parameter FNL, then the effect that has on this galaxy bias parameter that I was talking about, it looks like this. There's some scale dependence imparted to it that is hard to, basically can't be mimicked by other purely galaxy formation physics. So this is kind of a very nice, at least theoretically clean probe of primordial non-Gaussianities. The problem is that it's very observationally fraught, so these effects come in at very, very large scales, so multiples of close to 10, so that's what this figure here is showing. So the effect of this FNL of 50 is this black line here compared with FNL of 0, which is blue here, and so you can see the largest differences are really coming from very, very small multiples, so very, very large scales. And the issue is that these are the scales that are most impacted by observational systematics that are very, very hard to control. So this is kind of a direction that people are really interested in. It's very clean from a theoretical point of view, but very messy from an observational point of view. So I had something about other kind of more interesting features that people are looking for, but I think for the sake of time, we'll just wrap up here and say thanks. Yeah, exactly. So this is, I'll just say it now. So when we're looking for these kind of linear and logarithmic oscillations in the primordial curvature spectrum that you all know more about than I do probably how they come about. But we can search for them quite robustly. Actually, this is more observationally robust than the previous thing I was showing before, because they do come in at some smaller scales as well. Although there you do have to. And then you do have to worry about some theoretical, maybe nonlinearities that come in due to this. But as this figure is showing, the constraints that we have on the amplitude of these features are already doing better than the CMB and will only continue to do better as we get more and more data. And this is kind of one of the things that people are really excited about with next generation surveys, where we're going to be probing higher redshifts, which are more linear, so you have fewer worries about contamination from nonlinearities. And then we'll hopefully have very, very interesting constraints on the amplitudes of these features. Yeah.
These two discrepancies, one in the sigma 8 parameter and the other one with the so-called preference for negative neutrino masses, are they pulling the data in opposite directions? Or is it like the same cause with the suppressed omega?
So the DESI data alone that I've shown don't really weigh in on this suppression of structure, and
They constrain assays though.
they do, well, not the ones I showed. So the upcoming analyses will. The VAO measurements don't constrain assay at all. And actually in this figure, we're not including any of the data that has very low assay values. So it's only CMB lensing, which is consistent with the primary CMB measurement of the amplitude of the matter power spectrum. Actually prefers a little bit of a higher value of S8 of sigma 8 than the primary CMB does. And then we're also holding in these basically constraints on omega matter from the baryonic acoustic oscillations. So this actually has no information about the sigma 8 tension in it at all. If we were to include the low sigma 8 values, like if you look at, for instance, there are these galaxy lensing surveys that are the ones that are really preferring low values of sigma 8. You look at these, so there's these points here, which are measurements of redshift-based distortions coming from the BOSS survey, which is the predecessor to DESI. But like I said, these have about a 1 sigma projection effect in them, so looking at this is a bit misleading. You should kind of imagine they're shifted over 1 sigma, more or less. And then the ones that are kind of the tightest constraints that are low are galaxy lensing measurements of sigma 8. And these, there are a lot of kind of theoretical systematics in these and observational systematics that are not super well under control. And we're hoping that with DESI actually we can use DESI to learn about both theoretical systematics and observational systematics in these measurements in a way that will allow future galaxy lensing surveys like the Rubin Observatory that actually just took first flight on Friday to obtain more precise and more accurate constraints than these kind of current generation of galaxy lensing surveys. But if we had included these, we would get a neutrino mass detection of like 0.4 or something like that, EV.
But the point I was trying to make is that BOSS data or kinetic survey data, they want to suppress the power spectrum, whereas DESI data want to enhance the density power. And that seems to be sort of going in opposite directions. So,
So you'll have to wait for the DESI results on this to see if there's actually attention. So this is from but yes, if you just look at the BOSS data, then there's a slight preference for low sigma 8 that is at odds with the measurements of omega matter from the VAO combined with the
Thanks for the talk. A great overview, and thanks for measuring. Standard history of the universe and clustering experiment. It's very, very important to do that as accurately as you can. So you're doing your job now. I think theorists are not doing their job when they have statements like we have no idea what dark energy is. Stand. Because it's maybe convenient for trying to go to one person getting money for experiment. It shouldn't be that way. Experiments should be funded anyway. Maybe it's convenient for writing lots of papers. But the energy density of the vacuum is a physical object, which we know is there. You cannot believe in the standard model of particle physics without believing that this is a thing. We know that it was, 10 to the 50 times bigger than the current value in the early universe before electric fluid breaking, and that energy was then dumped into radiation when the electric fluid goes. So this is a physical thing that you can't just make optional. And so it's that. You're measuring it. And it is that unless you're kicking and screaming about overwhelming conflict that, into yet another complication on top of that.
I 100% agree. Yeah.
You don't get to say zero and somehow make it
Sure.
go with it.
Yeah, 100% agree. I guess when I said that we have no theoretical guidance for what dark energy is, I meant non-cosmological constant dark energy. writing down a functional form for like time evolution of current energy.
Yeah,
You
but
don't-
that's a strange way of stating things. It's like when I see a duck and I say, I have no theoretical guidance what that could be if it's not a duck. I usually don't entertain that possibility until I'm convinced that it's not a duck.
Right, so that, I should have, this comes back to your question about, the WCDM constraints by themselves, and actually I took a very similar perspective to you that, basically we have to have overwhelming evidence that there's some time evolution, and, that it was only, I guess I should have added more caveats to this statement, but if we are trying to hit for some time evolution, then we don't really know how to write down that time evolution, is what it is. Except for if 0 time.
Given that you actually, we are trying to model somehow, I think it's fine to use WNLK. It's just important not to confuse those with actual fundamental physics parameters.
Sure, yeah.
Yeah, but it's not that you can't write down a roll of
Yeah, so you can, there are ways like,
You can write those down, you can.
yeah, F of R gravity makes
You're
predictions for
sensitive about what we should expect or not, but it's not, it's.
the simplest models are basically ruled out though, right?
Well, but it's.
But they're insanely fine-tuned. You have to protect against radiative corrections, you have to make sure you evade fifth force in space.
Yeah.
All of that just to entertain something that we're not even forced to entertain right now.
We certainly have to be forced by the data into anything,
Yeah.
for sure, but,
But we're often presenting it as if it's like equally
We
likely.
can discuss it, more widely, the level of tuning, fields that can get around some of the tuning and all that, so I'm not an advocate, but I think we should be humble, we don't know. It's not something crazy the way, say, but it's fun to be crazy, it's.
I really disagree that there's nothing to do with humility, but with the scientific method. Like, I don't think it's humble to say there could be G's in the moon. It's just it's a very fine-tuned possibility that we don't entertain unless it's not like these are equally likely things. Like one is much more complicated than the other.
Well, there are people who have written some pretty clear axion models, and it's, I tend to be on your side of this, but it's not, I don't think it's as shock as saying that they're, outrageously fine-tuned.
I think there might be models that are not so fine-tuned, but it's always a complication on top of explaining why the cosmological constants.
Well, for sure, but the theorist deals with all sorts of complications.
How do you decide what to do, right? There's so many things you could be doing.
Well, I will decide what to do.